The following video is on the mean value theorem. The mean value theorem says that if f is continuous on a closed interval from a to b and differentiable on the open interval from a to b, then there is a value c in the open interval from a to b such that f prime of c equals f of b minus f of a over b minus a. Now this theorem looks kind of scary, but really what it's saying is the following. Remember that the word mean in mathematics stands for average. So what we're doing is we're taking the average value of this function over the interval from b to a. So we do the change in the b values over the change in the a values, which we also know represents the slope. Thus, if we look at the following picture, f is continuous over the interval from 1 to 3.5, differentiable from 1 to 3.5. So if we look at f of 3.5 minus f of 1 over 3.5 minus 1, we end up with the slope of this blue line here. What the mean value theorem says is that there's some x value c in between 1 and 3.5 such that the derivative at that point has the same slope as this blue line. Here's another example. Notice that this function f is continuous on the interval from -3 to 1, and certainly differentiable from -3 to 1. So if we take the y values and connect the line between those 2 points, the mean value theorem says that we're guaranteed a point in between x equals -3 and 1, such that the slope of the tangent line at that point is the same as the slope of this red line. We can approximate that it's about where this orange line is. The mean value theorem does not, however, tell us how to find this value c. It only tells us that such a value c exists. Let's look at the following example. So here I've denoted 2 points on the graph. And if I connect them with a blue line, we're looking for a point on the curve where we would have a tangent line parallel to this. But notice that no such tangent line exists. The reason for that is that we chose a function that's not continuous on the interval. F must be continuous in order for the mean value theorem to work. Looking at the following example, if we pick 2 points and connect the dots, we hope that we would find another point somewhere in between them that we have a horizontal tangent line. But we know that there's no such point on this graph with a horizontal tangent line. The reason for this is that our function is not differentiable in between -2 and 2. So once again, we need the function to be both continuous and differentiable on the interval, or else the mean value theorem won't work. Sometimes the mean value theorem tells us that we can have more than one point. So here we see a curve in between 1 and 3.5. We've connected the dots and we get the blue line as seen. Here we actually see that there's 2 points with tangent lines parallel to the blue one. That's okay. It's possible to have multiple values of c. The mean value theorem just guarantees that there's at least one value of c. Let's try a problem using the mean value theorem. Suppose that f of -2 equals 1 and f prime of x is less than or equal to 4 for all x. We want to know how large can f of 1 possibly be if f is both continuous and differentiable. Consider the closed interval from -2 to 1. The mean value theorem then says that f prime of c should equal f of 1 minus f of -2 over 1 minus -2. Furthermore, we know that the derivative of f is always less than or equal to 4, so f prime of c needs to be less than or equal to 4. So now we can plug in all the values that we know and solve for f of 1. So I get that 12 is greater than or equal to f of 1 minus 1. So 13 is greater than or equal to f of 1. So if f is continuous and differentiable, f of 1 must be less than or equal to 13. So the largest possible value for f of 1 is 13. The local cops also use the mean value theorem from time to time in order to catch speeding cars. Let's consider the following scenario. Cop 1 and Cop 2 have stationed themselves along Reservation Road, and there's a sports car that's speeding down Reservation Road. The cops know that they are 20 miles apart from each other. And at 2 p.m., Cop 1 clocks the sports car going past him at 30 miles an hour. At 2:10 p.m., Cop 2 clocks the sports car going past him at 25 miles per hour. We will let S of t be the distance past Cop 1 that the sports car has traveled t hours after 2 o'clock. So S of 0 is obviously 0 because the car is immediately in front of Cop 1 at 2 o'clock. The sports car traveled 20 miles in 10 minutes, but we need to know the hours because everything is being measured in miles per hour. So 10 minutes over x hours is 60 minutes over 1 hour, and we solve for x. We're left with x equals 1/6 of an hour. So S of 1/6 equals 20, because we know that the car has traveled 20 miles at time 1/6. The distance is continuous and differentiable, because the car didn't pop in and out of existence. So, by the mean value theorem, we get the change in S over the change in time equals 120. And we know that at some moment, at some time t, in between 0 and 1/6, S prime of c should equal 120. Notice, however, though, if S is the distance, we know that S prime should be the velocity. So that means the car was traveling 120 miles per hour at some moment in between the time that he was passing the two cops. Therefore, he was obviously speeding, even though neither cop saw him speeding. The mean value theorem does stand up in court, and the cops could give the guy a ticket, even though he wasn't speeding when he passed either of them.